Yo, what up, Sci Fam? It's your boy Nickel, and today we're gonna look at this experiment. This is called the greenhouse model experiment. You see, we have two stacks of glass plates that have a little bit of space between them where air can get trapped. But you can see there's 3 layers of clear glass, and then the bottom layer is a black layer of glass. So what we're gonna do in this experiment is we're going to leave these under the lamp for 10 minutes. Well, one of them at least we'll leave under for 10 minutes. The other one we'll only leave under for 5 minutes. So after 5 minutes, we'll take one of the stacks, pull it off to the side, and measure each layer of glass to see the temperature of each layer of glass. So we'll pull this off, take the temperature, pull this one off, take the temperature, pull this one off, take the temperature, and then take the temperature of our black piece of glass.
84, 86, 90. 84, 90, 103. 84. Thank you for doing the black one.
Then, that's after 5 minutes. 5 minutes later, so after 10 minutes, we'll do the same thing to this one and see what we observe in the data. So let's take a look and record the data for the first layer of glass stacks. So could someone share with me, in this experiment, what did the layers of glass represent? Rosella, what did they represent? It represents gases in our atmosphere. It basically represents our atmosphere. Now, if we look at the data that was collected, what role did the clear glass layers play in this experiment? What did they do? If we look at the data, what happened? What did these glass layers do? What do you think, Andrew?
They trapped and reflected heat like down on Earth.
Okay, they definitely trapped the heat. Now, what's interesting here is that yesterday, one of the groups tried to make 3 states, and they did a great job making 3 states. Well, more than 3, actually. So they turned Colorado or Wyoming into Idaho and Pennsylvania and another piece of broken glass. How did this happen, Gabe? What happened? What did you guys do? Why did this crack?
We were testing how high we could heat it up to, and it got really hot and broke.
Okay, we were trying to see how hot they could get this glass, and it just broke. Now, the reason this is interesting is because this actually helps us understand what's going on here in this experiment, actually. So I want to say thank you, but I'm not going to say thank you for breaking the glass, but thanks for the lesson at least. So if we looked at the first planet closest to the sun, does anyone know what planet that is? Closest to the sun? What is it? Let's get with confidence.
Mercury.
Yes, Dave's got it. Mercury. So when Mercury is facing the sun, Mercury gets really, really, really hot because it's facing the sun and it has no atmosphere at all. Then as it rotates away from the sun, the temperature drops. It gets really cold. And I'm talking about a fluctuation of like these temperatures are hundreds of degrees Fahrenheit. These cold temperatures are negative hundreds of degrees Fahrenheit. Yeah, it's the closest planet to the sun, and it gets that cold. It gets that hot, obviously. It's easy to think about why it gets that hot, but the reason it gets so cold because it doesn't have an atmosphere. So the reason that we did this experiment was to understand what's happening here on Earth. So if you guys could put your computers away, please, I appreciate it. And let's talk about what this is demonstrating. So obviously we use glass for our windows because it lets light in. If we look at the wavelengths of light, light is going to be a shorter wavelength than heat is. Heat is a longer wavelength. It doesn't have as much energy. So light has enough energy to go right through the glass, And the reason that black is because it absorbs all colors. No color is reflected, and so we see the color black. What that means then is that all of this visible light that comes in, it goes through the glass and it is absorbed by the black. It absorbs so much energy that it literally broke without these layers above it. So it absorbs heat, and then it gives off the heat, just like our bodies do. But if you go for a run, after your run, your body is emanating heat. Now, if you actually got hot enough, your body would start to glow, and it would turn into light because you'd have so much energy. And you know that because if you've ever seen somebody like try to do like metals or blacksmithing, you know, where they take like a piece of metal and they put it in the fire and it starts to glow. Or if you've ever taken a needle and you've tried to disinfect it with a lighter or something, the metal actually glows because it's not only hot, it has so much energy it starts to glow and have light actually. Now this heat, it doesn't have enough energy to go through the glass. We know that this is true because if we use those nice fancy infrared thermometers, if you point the thermometer at the glass, you can see your reflection in the glass. What that means is our heat is literally hitting the glass and being reflected back to the thermometer. So what's happening here is we were able to demonstrate that by checking the temperature of each of these layers of glass. We found that as we get closer and closer to the heat source, the layers of glass get hotter and hotter. So the final conclusion question then in our slides, I ask, well, using the takeaways from our experiment, well, so we know that the clear glass trapped the heat. So if we're talking about the clear glass being like greenhouse gases, how will increasing the amount of greenhouse gases impact Earth's temperature? What would happen then if we have more greenhouse gases? What do you think, Edison? It will get hotter. Now, the reason that I wanted to do this experiment, though, was to demonstrate that greenhouse gases themselves are not hot. What they do is they actually limit the amount of sun that can hit the Earth so it doesn't get as hot. But at night, like this morning when I woke up at like 5 a.m., it was like 40 degrees out. That's pretty darn warm. Now, this planet closest to the sun, Mercury, got negative something at night. Here it doesn't get that cold because we have these greenhouse gases that are trapping the heat. You see, the surface of the Earth warms up. Our air doesn't warm up. The surface warms up just like our body warms up and then heats up the area around us. Our Earth, the body of our Earth, the soil, the ground, the pavement heats up, and then it releases heat, and that heat gets forced back down to the planet because of the greenhouse gases. So at night, our temperature doesn't drop very low. So greenhouse gases help give us moderate temperatures because it helps moderate the heat leaving and entering our Earth. Now, without it, we would have huge fluctuations, and we wouldn't be able to survive here. Nothing would be able to grow because not only would harmful radiation hit our Earth, but also the temperature would be really, really crazy and dramatic. It'd be really hard to sustain life. Now, the main takeaway of this experiment is that two main takeaways. One is that we have greenhouse gases that trap heat. And the second is that greenhouse gases don't actually heat up themselves. I want to explain how they're able to trap the heat because there's actually a physical property about the molecule that helps it trap the heat. Because there's a lot of gases in our atmosphere, but not every gas in our atmosphere is considered a greenhouse gas. Okay, so if I catch this ball, if I throw it back to Max, throw it back one more time. If I catch that, I'm absorbing the energy that just hit me. And when I want to throw it back to Max, I have to push it back out. I think I was going to throw that time. So that's it. I'm not going to throw it. But this symbolizes the heat. I symbolize a greenhouse gas. When the heat comes to me, I absorb it, and then I push it back. Not all molecules do that. If I threw it to Gabe right now, he didn't see it coming. If someone didn't see it coming, they're not going to be able to catch it and throw it back to me. Not all molecules are going to move when heat energy hit them. Some molecules will. We call those greenhouse gases. So carbon dioxide is a greenhouse gas, and that's why we started with this experiment to demonstrate that there's a greenhouse effect on our Earth. It reflects heat, and only some molecules do that. And since we're learning about carbon dioxide in this part of our unit. That's why we started with this, to get an idea of the physical, because physical is like, our body. When we're physical fitness means you're moving. So the physical property of carbon dioxide is the movement aspect of carbon dioxide. I wanted to introduce it here in the greenhouse model experiment, and you'll find out more about it being a greenhouse gas and finding the culprit, and the Fizzy-Hot experiment. And then when you do the molecular motion assignment, you'll understand how carbon dioxide itself moves in the directions that it moves. So I appreciate you guys rolling with the punches there on this experiment. I realize it didn't go as smooth as we had hoped. But at this point, if you're done with this data, you can go ahead and finish the conclusion slide and go ahead and move on wherever you are in Sci-Hub.